Hello, this is a video lesson for Precalculus, Chapter 2, Section 2 of Demona Precalc book. Power functions with modeling is a subject. The objective is that students will be able to sketch power functions in the form of f of x equals k times x to the a, where k and a are rational numbers, but a will not be 0 for a power function. Power function is any function that can be written in the form f of x equals k times x to the a. And k and a are non-zero constants. K is what we will call the constant of variation. And a, of course, is the power. So you're going to have to be able to graph power functions and know about what each graph looks like according to the constant of variation and the power. So what you'll find is the different powers will show a different looking graph. And basically what you're going to have to do is you're going to have to experiment with the different types of powers you can have. Obviously there's positive and negative, but what you really want to focus on besides positive and negative powers are fractions or improper fractions. So look at what happens when the power is a fraction between 0 and 1, and not only between 0 and 1, but when the denominator is odd as opposed to even, and the numerator is odd as opposed to even, and same with improper fractions. Numbers larger than 1, but when you still have some sort of root involved along with a higher power. So take a look at all those different types of graphs and see if you can develop some patterns. Of course, this graph here is the fourth root of x, the power being 1/4, and if there's no number out front, then the constant of variation is 1. A monomial function is a function that can be written in the form f of x equals k, or f of x equals k times x to the n. So, where k is a constant and n is a positive integer. That's the big difference here. N needs to be a positive integer. And then this is also a difference right here. It's a special case. We consider that a monomial function. Remember, with just a regular power function, n could be any rational number besides 0, and now it's limited to positive integers. Describe how to obtain the graph of the function f of x equals 3 times x cubed is what that says. From the graph of g of x equals x to the n. Now this is similar to what you've had in the past with the same number, same power n. This is similar to what you've had in the past, but basically my warning here would be to make sure that you're reading the directions very carefully. In the past, you had, you were limited on what the power was. This right here says just compare it to x to the n. So over here, if I say 3x cubed, I'm not comparing it to x or x squared or anything else, but x cubed. You may think that's simple, and well, yeah, that's simple. It makes sense. But in the future, this may change. Right here, there may be an a sub n, which would mean compare it to whatever the constant of variation is times x to the power that it's raised to. So just always be aware and be careful to read the directions in what I want you to compare to. So basically, how do you go from the x cubed graph to f of x equals 3 times x cubed? Well, you've got a vertical stretch by a factor of 3 to the graph of x cubed. Would be one way to describe that. Remember, you always talk about what graph you're starting with and then how you go from that graph to the function that they're asking you about. And be aware both functions are odd. Review how you can tell if they're odd graphically. If you have a reflection in the origin, so every xy coordinate point becomes the opposite point, negative x, negative y, then you have an odd function. Algebraically, if you replace the x with a negative x, and when you simplify that, so if you basically check what f of negative x is, and you end up with the opposite of the function that you started with, then it is an odd function. All right, so one of three things will happen with power functions when x is less than 0. One of three things will happen. Either the graph will be undefined, like your square root of x or x to the 1/2, or f will be the function will be an even function, like x squared, or the function will be an odd function, like x cubed. And then what I recommend you do is start graphing some different graphs and notice what the graphs look like. Here's kind of a little cheat sheet for the first and second, or first and fourth quadrants. Basically, this is what you'll get when that k value is positive. These are the types of graphs you'll get when that k value is negative, or that constant of variation is negative. But do be aware that this does not include the entire graph in all cases. This would just be half of the graph, basically, for a lot of cases. But you know, if your exponent was 1, you just have a linear function. If you had an x value between 0 and 1, this blue graph is what you'd see. Again, these are all when the constant of variation is positive. If your x value is less than 0, the green one is what you'd have. And if your exponent was greater than 1, the red is what you'd have. And of course, you'll have more graph somewhere else depending on what the function is. Like if it was x squared, you'd be coming up over in the second quadrant. If it was x cubed, you'd be going down into the third quadrant, and so on. So study that, graph some different functions, and just see what they look like. Just test yourself. Do you know what x to the 2/3 would look like? Graph it and see if you're right, that sort of thing. The next thing I want to mention that may cause some confusion is direct variation versus inverse variation. It's basically terminology used to describe different power functions and some other types of functions. But a power function formula with positive powers are statements of direct variation. So when you have positive powers, you have direct variation involved. And then when you have negative powers, you have inverse variation involved. So power function formulas with negative powers are statements of inverse variation. Basically, unless the word inversely is included in the variation statement, then the variation is assumed to be direct. It's the easiest way to remember. So unless the word inverse or inversely is used, then it's going to be an example of direct variation. So for example, if I were to say that the circumference varies directly with the radius of a circle and constant of variation 2 pi, well, I'd be saying that the circumference of a circle varies directly with the radius of the circle and constant 2 pi. So the constant you're always multiplying by, and then if it varies directly or is proportional to or does not use the word inversely, then basically the variable is on top of the fraction, if you will. Just keep in mind when you're working with problems where you're actually solving a problem, there's oftentimes a constant that's not considered, or that's that you need to find first. Another example is I might describe the force of gravity as force equals or actually maybe I'll give you the, I changed my mind again. I'll just say it. The force equals some constant. Let me start over. Force is inversely proportional to the square of the distance an object is from the ground, um, and some constant k. So when I say inversely proportional to the square of something, some distance d, well, that tells you that the force is inversely proportional. That means that you say 1 over d. But I didn't just say d, I said the square of the distance. So that tells you you'd square that variable. And some constant k is what I said, so then you multiply by some constant k. So you could put the k on top, or you could set it off to the side. So those are just a couple examples, but the biggest thing is if I use the word inversely, then you're putting the variable on the bottom. If I don't, then you're putting it on top. Now I'll go through a couple examples. I'll go through a couple examples from your text, so you might want to just read the books. I'm not going to write out the whole problems, but if you're given a set of data, and you know that y is a power function of x, so this would be like numbers 49 and 50 in your textbook. You can try to plug that data into your calculator. Remember, you'd go to Stat, Edit, plug the data into your list 1, list 2, make a scatter plot, and basically there's a power regression function as well. So, whoops, if I go to Stat, over to Calculate, and scroll down, you see these different, there's a linear regression, quadratic regression, cubic, quartic regression models, another linear regression, natural log regression, exponential regression, power regression. That power regression function is what you'd use when it says the data given for y as a power function of x would give you the constant of variation in the exponent of your power function for you. However, sometimes you're given negative numbers for y, and your calculator won't calculate those, so then you have to use some sort of algebraic model. And what I want to do is I just want to review a little bit of what you do to solve those, since we don't have a lot of practice with logarithms. I need to remind you of those. So basically, I'm just going to take 2 points from that set of data. I'll take 2, 2, and 4.5, or as I like to call it, 1/2. You know what I mean? So that's what you're given. And basically, you know your power function is y equals k times x to the a. That a is not going to show up well. There we go. Times x to the a. So what I'm going to do is I'm basically just going to write 2 equations with 2 unknowns. So I'm plugging the 2 and the 2 in for y and x. So 2 equals k times 2 to the a. And then I also plug in 4 for x and 1/2 for y. So I know 1/2 equals k times 4 to the a. And then in this case, I don't know outright what k is. So what I'd have to do, or one option would be I could solve for k. Like over here, maybe I'll solve for k. And then I'll plug that in for the k over here. So then 1/2, 2's and a's it doesn't like very much, would equal 2 over 2 to the a times 4 to the a. Come on, catch up. And from there, I just need to simplify. I've got a real nice situation here because I can write everything as power of 2 if I want. And so I do want to do that. And maybe at the same time, I'll bring this 2a up. So I'd have 2 to the negative a. And then this 4 to the a, well, 4 is 2 squared. And I can raise that to the a, which is the same as, and again, you might not write this many steps, but hopefully this helps you understand what I'm doing. 2 to the negative a times 2 to the 2a. And remember, when you have the same base, you can just add exponents. So maybe what I'll do at the same time here is I'll divide by 2 to get 1/4. That got rid of this. And then combine these. Well, negative a plus 2a is just a. And, you know, right here you probably just know what you raise 2 to get 1/4. So you would probably just know that a is negative 2. But if you didn't, remember with logarithms now, if you're looking for the exponent, you just take the same base as what you have here. Remember, this is the base, this is the power. You use the same base on your logarithm, and then if you're looking for the exponent, that's what you're taking the log base 2 of. And so if you type that in your calculator, depending on what kind of calculator you have, you might be able to just plug it in exactly like that. Otherwise, you'd use your change of base theorem where you could use log or natural log, common log or natural log of 1/4 divided by the same log of 2, and you'd get, whoa, too many. You'd get negative 2 for your answer. So there you have A. Just come right back over here, plug that back in. And of course you'd bring that, it'd be the same as bringing that up. So it'd be 2 cubed, which would be 8. So y would equal 8 times x to the negative 2 for your answer. So without making this video too long, I'll just tell you for number 50, 50 is actually even easier because you're given the initial value, or you're given, you're given the value when x equals 1. So you're going to be basically taking 1 to the a. Well, 1 to the a is just going to be 1, so you'll be able to solve k very easily by plugging in the first coordinate they give you for x and y. That'll give you k, and then plug in k, and and the second coordinate point they give you to get a. You need to use the logarithm again, but at this point, you're experts at that. Right now, I'm basically just going to read some examples from your homework on 51 through 55. I'm just going to read some examples and write down what I'm reading as I read it, if I can handle doing that. So this is where you're just trying to write out the equation being described. So for 51, the volume of an enclosed gas at a constant temperature varies inversely as the pressure. So that tells me the pressure will be on the bottom. So it said that the volume of an enclosed gas at a constant temperature. So I'm going to have temperature involved. It's a constant. So I'm just going to put temperature up here. But keep in mind there's always possibly another constant that you need to multiply by. So that's the formula I'd be looking at. And then the problem continues. If the pressure of a 3.46 liter sample of gas, so that's volume, 3.46 liter, okay. If the pressure of that sample of gas at a temperature of 302 is 0.926 atm, what would the volume be? Okay, so now we're looking for what would the volume be. Remember, we have that constant temperature. What would the volume be at a pressure of 1.452? And I'm not going to go and solve the rest of this, but basically you solve for k here, plug it in here, and then find your answer. But that would be the setup. The only difference would be, um, the only difference that might come later on is it might say varies inversely. Or it might say varies directly. Excuse me, this one did say it varies inversely. It might say varies directly, which if it said the pressure varied directly, the only difference would be it would go on top. So just don't forget that there's always this constant of variation that you need to check for. And it should make sense. Like, you should know you need something else if the numbers they give you don't equal don't equal out in the equation that you've written. If that happens, the odds are you're missing that constant. So enjoy the lesson.